Well, I hope all of you had a great weekend. It's a Monday, and so let's get cracking. Before I start on with the lecture, let me say something. This is how you knew the lectures would follow. But what I did was, when I was talking of here alkoxide based process applications, thin films, vapor phase route, what I did was I brought these two topics straight up here, because all of them deal with thin films. And hence, in the final analysis, by the end of the lecture, you will see there are some rearrangements. But so be it. Today, I shall start off with characterization of ceramic powders in all ways. Now, let us look at ceramic powders. But before I go to powders, let me define some markers. Let's say this is micrometer scale. This is 10 to the power of minus 3, 10 to the power of minus 2, 10 to the power of minus 1, 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. Viruses are somewhere over here. This is where viruses are. Now, this range, let me draw a line and help you. This is where viruses are. Today's paints, there is the ones that are weather coat paints, they are here, paints. These are the weather coats which uses ultrafine nano sized titania. There are paints which are also up here which are not that fine. Tobacco smoke or smoke is somewhere up here. The bacteria are somewhere on this scale. The red blood cells are somewhere over here, and in this zone we find cement, sand, right up to a millimeter or so. So, what we are talking of is ceramics at this end, and again ceramics at these two ends. Ceramic powders can come in various shapes. For example, all of you have played around with chalk. Chalk is nothing but calcium carbonate. There are chalk dusts which fly off, they keep suspended in the air, and so they are little larger than tobacco smoke. But more than sizes, the shapes are important. Most of the ceramic powders have a rough shape. In order for packing, for improved packing, we require ceramic powders of certain shapes. Let us say, as an example, let us start filling up. Say we have got ceramic grains of this diameter. Here is a hole. So, let me try to fill it up with a smaller one. Yet there are more holes. A rough rule of thumb is, if this is R, then we require R by 4, which is this one, and R by 8 powders to make sure that there is no gap. A rough rule of thumb is this should be 40%, this should be 20%, but this should be 40%. However, this presages or presumes that the powders are spherical. Normally they are not. So, how do we know? Because we are always looking for very dense ceramics, be it your coffee cup, or for those of you who have most of you kids have a motorcycle and there is a spark plug, I need that firing plug alumina which is 100% dense. So, there they had to use different particle sizes of the ceramic powders so that they could have a dense material. How do we do it? One straightaway technique is microscopy and optical microscopy. This can be done very simply. Let us say I will take a sellotape and then spray the powder on the sticky side, dust it off and then put it under a microscope. A microscope has a magnification or maximum magnification, if I am very careful, of 800x. So, 1 millimeter divided by 800, that is its maximum magnification. But getting that magnification, I said 1 millimeter is the smallest division divided by 800, which brings it to almost 1 micrometer level. Doing this is going to be tough because this is your sellotape. You have the powder sticking out on this sellotape out here, and your eyepiece is here. The distances will vary, and as a result, achieving this 800x magnification is almost impossible. In an optical microscope, I would normally settle for 400x magnification for well prepared samples. So, these samples can be this, it can be any shape or sizes. Now, the question comes in, what if they are finer? What if they are finer? This I will take up much later once I have dealt with the basic techniques. Now, in an industry, during a production run, you have to realize that very simple crude detection techniques are followed. If somebody, let us take the case, let us take an imaginary case, some company is making pig iron. They are not sure if the amount of lime added is correct. So, they have to take it off, analyze it, and most of the companies do not have the facility, and that is also time consuming. So, basically in any industry, the eye, what you see, the feel of the material in your hand are frequently things which give you the best results or best observations rather. So, now the crudest but very effective sizing technique of ceramic powders is sieving. I guess all of you have seen your mother sieve the atta before she prepares the dough. She has a plastic container which has a mesh. She puts the whatever she has brought for the market, then shakes it. The finer powders fall down to the bottom, while the coarse, bran and those things, they stay on top. In ceramics, what we do is, we have sieves, multiple sieves sitting on top of each other. Each of these sieves are detachable, by the way. Each of these sieves are detachable. Now, this sieve is the coarsest, while the sieve at the bottom, this sieve is the finest. The whole idea is, put the powder over here and shake it. As you shake, the powders which are finer than the holes over here will fall down here. And during this process, powders will start collecting here according to size fractions. Now, let me start now putting in numbers. Let me say this is 50 BS sieve. Let me say this is 100 BS sieve. Let me put this as 200 BS sieve. This is 250 BS sieve, and this is, let me put it as 300 BS sieve. What would it mean? These 50, 100, 200, 250, 300, these indicate the fineness of the sieve. This sieve is the coarsest, this sieve is the finest. Now, yet I am not yet going to define what is BS. Suppose we are shaking. So, there is some powder which is collected over here. There is some powder which is collected over here. Some powder which is collected over here. This is collected over here, and this is collected over here, while rest of it has stayed back over here. In ceramic industry, this powder is written as minus 50 plus 100. It means this powder is finer than 50 BS, but coarser than 100 BS. This powder will be minus 100 plus 200, because it passed through 100 but could not pass through 200. This one would be minus 200 plus 250. This one would be minus 250 plus 300. And this one would be minus 300. Now, this 300 sieve corresponds to 44 micrometer. This is 44 micrometer. If you look at the ASTM standards, I am deliberately not putting in everything because these are available in standard books. You will find out what does these words BS mean. BS is Bureau of Standards, but then what do these mean? Each of them correspond to a particular size in micrometer. And the way it is defined, if this is 1 inch, looks like 1 inch to me. Yeah, looks like 1 inch to me. How many wires are there of that mesh in that 1 inch? And that defines this particular number. So, when in ceramic industry they want to make, say, a cup, the cup that from which you drink tea, they want to ensure that the powders are properly distributed. As I had said, one should have this ratio of powders. What they would do is take the raw materials, grind them very well, and take these size fractions and mix them properly so that maximum packing occurs. I had said earlier, long back in the early stages of my lecture while I was covering sintering, that the better the packing in the green form, the more easier it is to obtain a dense product. Because if packing is good, then diffusion distances are small and one has good control over the sintering. So, this sieve analysis is a good way of characterizing ceramic powders. However, it works only up to 44 microns. In some cases, if you take 400 BS sieve, you can go up to 37 micrometers, but then whether you are using 400 BS or even 300 BS, which is 44 micrometer, after sieving the sieves tend to clog, and we get at the last stage over here an entirely fallacious size fraction because the finer particles have jammed these pores. So, if we use 400 BS, the situation gets very tough, but yet at times people do wet sieving, with ultrasonic agitation to stop the blocking of the pores, and using wet sieving powder size control up to 2 micrometer has been done. But then it is a very time consuming, very expensive process for getting different size fractions down to 2 microns with wet sieving. So, here in sieve analysis, we are not really looking at the shape or the size of the powders, because a grain may be this, and this has slipped through the sieve. So, this may be say 10 micrometers, but this can be 100 micrometers. But because this grain is elongated, it has slipped through. So, sieve analysis does not give you any idea of the shape or the size fully, but yet it is a good starting point for knowing the shape or sizes of the powders in the industry. Another very delicate method will be sedimentation technique. I do not know how many of you as kids have had fun. We would take a bottle, put some clay particle in it, put water and shake it, and then let it stand. We would see the coarse particles fall down very fast, with the finer ones staying suspended longer, and finally they would also fall down. So, obviously, if someone is looking at sedimentation rates, then they would be able to know the powder size. If we presume that we have a spherical particle of density dP, diameter A, and this is let fall in a viscous liquid of viscosity eta L, and density of this dl has to be lower than dp, because if dl is higher than dp, the particle would float. Now, when we have taken this particular particle and have let it fall in a liquid, it is falling over here, it will keep falling and achieve a terminal velocity let us say nu, because it is falling due to the action of gravity, but then the viscous liquid is also impeding its fall. They would balance and it would achieve a terminal velocity of nu. In this process, we are assuming that the flow is laminar. That is, as the particle falls, it is a typical laminar flow. There is no turbulence. There is no turbulence. This laminar flow occurs when particle Reynolds number is less than 0.2. This Reynolds number Re is calculated from the equation this is the Reynolds number, and the terminal velocity is related to Stokes' equation by G is acceleration due to gravity. The time T for settling at height H is this is the time at which it settles at a height of h is given by this particular equation. There are various commercial apparatuses which make use of this Stokes equation, the terminal velocity, and from here we can get the particle size. At times what they do is this to speed up centrifuging is done. What happens when you centrifuge? The value of G goes up, the time reduces, and hence from here we can determine the particle size depending on the time it takes to settle at a particular height L. Another industry standard technique is electrical sensing technique, and this is also a very simple material. You have got a beaker or a container in which you have got a dilute suspension. This is being constantly stirred. You have got a magnetic stirrer. This is a liquid. You have an electrode here, you have a counter electrode over here, and this one is encased in a tube with a small hole. And this goes to a vacuum pump. I have just put in it arbitrarily because it depends on charge. Now, we have got this apparatus, we have got a dilute solution which is being stirred, and then we pass a current through it. If this is a suspension which is conducting, then the vacuum pump is turned on. This is a very dilute solution. At times, this space will be occupied by a ceramic particle. What will happen? The current flow will drop. So, if you are plotting the current as a function of time as you are evacuating, you will find that if this is the time, this is the current, you will find something like this. Nothing regular, it varies. What are these spots? Why is the current low? Because this particle is blocking the orifice. Use of the vacuum pump helps in dislodging this particle, so the current drops and then goes back. But by this particular technique, we can, and by varying the aperture, we can have an idea of the sizes of particles. Another technique is basically light scattering technique. I guess most of you have seen that if in a closed room through which a ray of sun is coming, if there is dust in the room, it shows up in the sunlight. Why? The sunlight is coming through a narrow orifice, the particles are diffracting the light of the sun, and you see an area which is lighted up even though the particles are finer. So, what happens? Light comes in, a very narrow defined beam of light, and it passes through a beaker which has a very dilute suspension. Depending on the particle size, what will happen? The light will diffract. If the particle size is large, this is finer particle, this is a larger particle, the diffraction will be lesser. This is well known, you have studied it in your school days. Now, over here we have a screen on which there are photo detectors. These are photo detectors. We can count off as a function of time what is the light intensity at each detector away from the axis, and which will be proportional to the diffraction. From this technique also, light scattering, we can find out the particle size. Today, this light scattering has become more of a laser scattering, because laser beam need not be focused. It is already focused. With any other source of light, it is a divergent light. We have to focus it, more additional optics are required. So, laser scattering is a very important technique for determining the particle size given, and there are many such equipments in the market. You can simply Google laser scattering and find out what are the ways it works. Now, I have said that I do need to know the particle size and shape and the distribution of particle size and shape, so that when I am fabricating a body, I have the maximum possible packing. But what we have not as yet dealt with is, let us say I take a piece of brick, a hammer, I break the brick into two parts, break it still more and make it into a fine powder. I do not know if those powders are porous, if basically their density is specific to any powder, because each chemical compound will have its own fingerprint density if it is fully dense, at least in a theoretical sense. So, after having dealt with sieving techniques, after having dealt with sedimentation technique, laser light scattering technique, all of which are used in the shop floor of the industry, I am now stepping back. I am not going forward. I am stepping back now to say, hey, fine, you have told me how to do it, but what about the powder itself? Is it dense or is it porous? So, one of the first things that we have to do is measure the density, because each chemical compound has its own density unless it is porous. So, what we do is we take this ceramic particle, break it, further break it more, with the hope that any pore which may be here will finally come to the surface as I break the powder into finer and finer grains. Now, how do I measure the density of these powders? Because the density will tell me if I have got the product which I want. Let us say I know the density of alumina, I know the density of aluminum nitride, I know the density of silicon carbide, I know the density of silicon nitride. All these are known, but suppose I want to mix aluminum nitride with silicon nitride and then form a dense body. I will have to know whether the aluminum nitride is porous. I have to know whether silicon nitride is porous, because I had told you earlier that porosity reduces sintering rates, because at times the sintering wave front get blocks at the pores. So, how else to know it than other than density, because densities of each product is very well known. If the material is porous, then the density of the material under consideration would be much lower than its mother product. And how you determine the density? You were taught in class 10. But still I have to rehash it because this is where everyone makes a mistake. What you had were tubes like this. With a plug. With a plug like this. This is an experiment you have done, but just to make sure you can recapitulate, I am going to describe it. This is called a pycnometer, in case you have forgotten. First is weigh empty pycnometer with the basically seal. Then fill it up with some of your ceramic particles and weigh the pycnometer. Let's say this is W1, this is W1, to weigh. Now this is no longer empty pycnometer. With the seal and ceramic powders. W2. So W2 minus W1 is weight of powder. I have to determine the density of this powder. Then fill this up pycnometer with liquid. And press it down. The extra liquid will go out from the top. 3. Weight of pycnometer plus particles plus water or solvent required to fill empty space. Because before the solvent was put in, the most of the pycnometer part was empty. And fourth, remove sand, clean up pycnometer and fill with solvent whose density is known. So, W2 minus W1 is weight of ceramic powder. Of course, I have written over here. Then this is W3. W3 minus W1 is weight of liquid required to fill up. So, we have W2 minus W1, this is the weight of the ceramic powder. To fill the pygnometer up, whose volume is well known, W3 minus W1 will give you the weight of the liquid, and from the, because you know the density of the liquid, you can find out the volume of the liquid. So, using the Archimedes principle, which I am going to leave it to you because you have studied in class 9, 10, 11, you can use this data to find out the density of these ceramic powders. This is something that you have been doing since class 9, and there is no point, I would not rather wish to burden this lecture with calculation of density of ceramic powders using pygnometer. However, so far I have covered how to get an idea of the size, shape, not really, the density, yes, but one of the most important factor in ceramic processing, which is pore structure. Let us say we frequently find this is an idealistic drawing, so never mind. Pores. At times they are interconnected, at times they are just pores. This makes the grains very, very porous, and as a result alters the sintering procedure. So, the first question is, how do I measure the total porosity in my ceramic? One of the ways to do it is mercury over here. What is done? There is a high pressure container which has got mercury in it, and porous these are good enough. This is the mercury, these are the porous surfaces, and pressure is applied. mercury will flow into these pores depending on the pressure. And the pressures up to 200 megapascal are available, though at times we go up to 400 megapascal. The mercury flows into the pores, and after that, if you depressurize and then weigh the particles, obviously the weight would be much higher than the weight of the pores. Since you know the density of the mercury and the particles, you can from there find out the porosity. Normally, what is known as, there are graphs like this. Depending on the pore diameter, more and more penetration occurs. If you are looking at numbers, this is 0, this is 1, this is 1.0, no, sorry, this is 0.01, this is 0.001, and this will be 0.1. And these are microns. This is 0.1, 1, 10. These sorts of graphs are there which indicate what is the porosity of the material. The other question that comes is surface area. This is done by adsorbing gases like say nitrogen and measuring how much adsorbed, and from there the specific surface area. For example, what I would do is take the particles, cool it down to cryogenic temperatures, liquid nitrogen or lower, evacuate it so the surface is cleaned, and then fill the chamber up with nitrogen. Nitrogen would adhere to the surface, equilibrium condition, and then pump out the nitrogen. Pump out the nitrogen, warm the vessel up and find out how much nitrogen is degassing. The amount of nitrogen which is degassing is proportional to the surface area. Well, let us take a break now. That gives you a specific surface area. But before I quit, I would say that an excellent source book is James Reed's this book, Introduction Lag bhi na.